Hello guys, this is Rick from Mathics, and today we're going to be doing the number 20 from the AMC 10B of 2021, or the number 15 from the AMC 12B of 2021. Now, this problem is quite intimidating, because just look at the geometric figure they give us. Like, what the heck is this shape? It's a pentagon, but with a bunch of additional line segments on the inside. And this overall will scare almost any viewer on this test. However, as I'm about to show you, the approach to solve this problem is actually quite simple. And this scary image that this problem is giving off is just to overcompensate for the fact that it's quite easy to solve. So without further ado, let's just get into this problem. The figure is constructed from 11 line segments, each of which has a length of 2. The area of pentagon ABCDE can be written as root m plus root n, where m and n are positive integers. What is m plus n? So the problem is quite simple in its context. We have 11 line segments, each with a length of 2, and together they form this pentagon ABCDE, which has an area that can be written as root m plus root n. We pretty much have to figure out its area to get m and n, and we will add those to get our answer, which is going to be one of the following answer choices: A20, B21, C22, D23, or E24. So from here, the first thing worth noting is that this shape is really hard to deal with. So let's try to simplify it. All these lines on the inside are kind of complex, and they kind of confuse us even further. So let's just draw a version of ABCD that doesn't have all these lines to mess us up. And maybe that'll make our problem a bit easier to deal with. So here I made a copy of pentagon ABCDE, except without all the clutter on the inside as the original figure had. Now, looking at this diagram and considering it's exactly the same as our original diagram, which we knew everything about, we can actually just fill in some lengths and angles for this pentagon as well. First, we know that each of the side lengths of the pentagon is 2, because the problem tells us that all the 11 line segments in the original pentagon is 2. And we have all these original line segments except for the ones on the inside. So each of these line segments that make up the perimeter of the pentagon has a length of 2. So I can write 2 here, 2 here, 2 here, and 2 here, and 2 here. Second off, looking at our original diagram, we can actually deduce some angles. So since all these line segments are 2, we know that this triangle here is an equilateral triangle. And the same can be said about this triangle here. And this is because it's made of 3 line segments of equal lengths. So 3 sides of equal lengths means equilateral triangle. Now if it's an equilateral triangle, that means that the angles are 60 degrees. So the sum of the 2 angles, which would form angle AED, is 120 degrees. By symmetry, this angle is also 120 degrees. So now things have gotten a little bit more interesting. We have this pentagon with 2 angles of 120 degrees, and all sides are of length 2. From here, we can do something pretty simple, actually. We can connect points A and C by a line segment. And we can do the same with points A and D. So now we form 2 triangles, triangle ABC and triangle AED. And each triangle, ABC and AED, is actually a special type of triangle. If I just draw one of these triangles to the side, we can see that we're dealing with an isosceles triangle. So since this is an isosceles triangle, because both of its sides are the same length of 2, we know that these two base angles are equal as well. And since this vertex angle is 120, these two base angles, which are the same, must have to add to the additional 60 degrees in order to get the 180 degrees on the interior of a triangle. So if this angle and this angle are going to add to 60 degrees, and we know that they're equal due to the properties of an isosceles triangle, we know that the measure of each of these angles is 30 degrees. And from that, we can drop a perpendicular which bisects this vertex angle to form a 60-degree angle, and we got a 30, 60, 90 triangle. Since the hypotenuse is 2, the height would be 1, which means that the base of one of these triangles would be root 3. And just like that, the base of the other triangle would be root 3 as well. So combined, this length is 2 root 3. So line segments AC and AD each have a length of 2 root 3. But wait, we can actually figure out some of these areas as well. Since we knew pretty much every length along with the altitude of this triangle AED or ABC, we can pretty much compute its area. We know that the height of the triangle is 1 due to the 30, 60, 90 properties and the hypotenuse of 2. And we know that its base is 2 root 3. So the area of a triangle is base times height over 2. So it's 1 times 2 root 3 by 2. However, we need to, in order to compute for the area of the total pentagon, we have to compute for the area of both triangles, which means that we're going to have to multiply this value by 2 as well. Which means that the combined area of both triangles is 2 root 3. So now that we've computed for the combined areas of ABC and AED, in order to find the total area of the pentagon, we just need to compute for the area of ACD. So if I just take this out below, just triangle ACD, well, we don't know too much about it, but there's a couple of things we can figure out. First is using the 30, 60, 90 triangles derived from our 120 isosceles triangles, we know that the side length of each of these bases is 2 root 3. And these bases represents side length AC and AD respectively. So we know that AC and AD respectively are 2 root 3. This means that this triangle is isosceles as well. Furthermore, since from the original diagram we know that all of the exterior line segments had a length of 2, we know that this base CD has a length of 2 as well. That means that this is an isosceles triangle once again. So this means if we drop a perpendicular from A to CD, this perpendicular will bisect line CD. And if we call the midpoint at which this bisects as M, we can figure out the lengths of CM and MD to be 1 and 1 respectively, since the side length of 2 will just get bisected. So we have this triangle's ACD, we dropped the perpendicular to M, and now we have two smaller right triangles, AMC and AMD. So since it's a right triangle, and we know the hypotenuse, and we know the base of each of these right triangles, we can easily figure out the height. Using Pythagorean Theorem, we know that AM squared plus 1 squared, 1, is equal to 2 root 3 squared. 2 root 3 squared is 12. So just like that, we know that AM squared is equal to 11. Or AM is root 11. So now we know the height of triangle ACD, root 11. Furthermore, before that, we already knew the base of ACD to be 2. So we have the height and base of triangle ACD. So to compute for the area, we would do 2 times root 11 over 2. Which would simply give us root 11 as the area for triangle ACD. So now we know for the area of ACD, and we already computed for the combined areas of triangles ABC and AED. So now that we know ACD, we can just add up the two areas that we computed for. One area which represents the combined area of ABC and AED, and the other area that represents the area of ACD, and this will give us the area of the total pentagon. So doing that, we get 2 root 3 plus root 11. Here's the thing though, we're not done, because it says that this area can be written as root m by root n, where we can clearly see that root m and root n have no coefficients, which means that we're going to have to convert 2 root 3 into a form in which it has no coefficients before the radical. This can be easily done by converting root 2 to root 4 and just multiplying by root 3 once again, which would give us root 12. Taking the root 11 down, we get root 12 plus root 11, which are, in this case, our respective m's and n's. So 12 is our m and n is our 11, or vice versa. It doesn't make a difference at this point. So adding them together, we get m plus n is equal to 12 plus 11, which is equal to 23. Or option D. So as you can see, even though that this is a number 20 on an AMC 10 exam, or a number 15 on an AMC 12 exam, there is nothing too crazy about this problem. In fact, we literally just used simple 30, 60, 90 identities from this 120 angle, and for the other one, we just used Pythagorean Theorem. Both are pretty low-tier geometry concepts. Nothing fancy, nothing too excessive. However, the biggest part of this problem was just not getting distracted by all this clutter on the original diagram. If you get caught up on this clutter, no matter how much you work on it, this diagram won't help you whatsoever. So the key thing to recognize here is how to just simplify this diagram into what's relevant. And once you can do that, this geometry problem becomes fair game for anybody who knows these simple concepts on area and 30, 60, 90 degrees. So this goes to show, a lot of problems will have a lot of fancy additions to these problems. However, a true problem solver would be able to notice what's relevant and what is not relevant and use that information accordingly to solve the problem.